Chapter 9 introduces the idea of non-parametric statistical testing with ranks through the Wilcoxon Rank Sum Test and the Wilcoxon Signed Ranks Test. So two different tests. In part A, we'll do the Wilcoxon test. But first, I want to talk about ranks. So many non-parametric procedures involve ranks. So let me just pop over to R and talk to you about ranks. So I just made up some data values that I put in a vector called y so that I can just call rank of y on that vector, and then it tells me the position in a sorted order for each of the values in the vector. So 73 would go in the 10th position, 14 would go in the 6th position. The thing that's ranked 1 is 3 here, and the thing that's ranked 2 is the second largest one, 6, and then the third largest one, 9, and so on. If you want to get a little bit nerdy about it, the rank is the order of the vector. So order tells you what order to put the indices in, and if you ask what order to put the ordered indices in, that would be the rank. There's a little bit more about that in the book if you want to dive a little deeper. I want to introduce some ties in the rank. So look how I'm appending the vector y with an extra copy of the second element and then 2 extra copies of the 7th element. So I have duplicates and then I have triplicates. So let me just do that and then rank the vector y. And you can see that what happens is we start to get some fractional ranks. So here is the new copy of the second one that I added, which is twinned here with the second one with a rank of 8.5. And then the 7th one that I duplicated here at the end, that was ranked 6, and it's tied with this one. So any duplicates are going to end up with a 0.5 fractional rank. But then when you have triplicates, you end up getting a whole number of ranks again, and then it would alternate with even and odd numbers of ranks. So when we rank things throughout the book, but especially in this chapter, we're going to use the rank command. And I just wanted you to know what that means and that you might end up with some fractional ranks. Okay, so now I could talk to you about the Wilcoxon Rank Sum Test. Some people say Wilcox test, other people say Rank Sum Test, some people say the whole thing out, Wilcoxon Rank Sum Test. So it's a test between two populations. So it's sort of like the non-parametric analog of some of the chapter 5 stuff that we did with 2 sample t-tests. But it's not a t-test, it's non-parametric. So I have NYY values that are IID from some distribution that I'm going to notate as FY. And I have X values that are IID from some other distribution that I'll call fx. And what I want to know is, are these distributions the same or not? But the test targets averages or means. So the actual hypotheses are really just targeting, is the expected value of y equal to the expected value of x or not? Okay. And so it's kind of like the permutation test is targeting a very similar property, although it's more focused. With the permutation test, you can pick to focus on anything you want, whereas the Wilcoxon Rank Sum Test is really just looking at means. So like the permutation test, from chapter 8, the Wilcoxon test works on the combined sample of size n, which is ny plus nx. Okay. All right, so here is where the ranks come in. Let Riy and Rjx denote the rank assigned to yi and xj in the combined sample. Okay, and that's for all I in 1 up to ny and j in 1 up to nx. Okay, so let me, some of these things are actually easier to explain in code than they are to write down. So if that didn't make a tremendous amount of sense, I hope it will in just a moment. All right, forget the fake y vector we were working with before. Here is a y vector and an x vector that comes from a data set from the Washington Metro, which is a subway rail system in Washington, Virginia, and Maryland. And y has the number of riders who said they used a prepaid paper fare card, which are now defunct in that metro system, in a Virginia stop, and x is the ones who said they used a prepaid paper fare card at a Maryland stop. Okay, so two different vectors, one to know if they have the same mean, do not want to assume any distributions, just that they're IID, want to see if their means are the same. So let's extract just length. So we have ny is length of y, and nx is length of x. Okay, so that's easy so far. Combined sample. So I'll call that yx. That just combines the y and the x's. And its length is ny plus nx. Okay, and then I'm going to rank the combined sample. So I'll call that ryx, rank of yx. So that's what it means to rank the combined sample, to get these ri's and rjx's. Making a mess here. Okay. All right, so that's sort of the setup. There are several common test statistics that are used with Wilcoxon Rank Sum Tests, but most involve what's called R bar, or you could also call it R bar Y, because it is the sum of ranks. It's called the rank sum test. So we're going to probably sum up some ranks at some point, and that's what we're doing now to develop the statistic. So the statistic is the sum of the ranks for the y variables. I'm using a bar. I know we use bar for averages, and we could make this an average. We could divide by ny, but people don't. But I'm going to call it R bar anyway, because it's a compact way of keeping track of things. You could sum the ranks of the x's instead, so that would be another test statistic that would be totally legit and would turn out very similarly. Like I said, there are many common test statistics, and I'll show you yet another one later. So there's this one. One thing that trips people up about this is that they think I'm throwing the x's away, but I'm not really throwing the x's away. The x's affect the ranks of the y's, in the combined sample of the y's and the x's. So it's kind of like in this statistic, the x's are in the negative space. They affect the ranks of the y, so even though we're only summing up the ranks of the y, the presence of the x variables or data points are still felt in this statistic. Okay, so going back over to R, the test statistic, I got to take the ranks of just the y variables. So that's going to be R, y, x, but just the first n y of them. It's rx, ryx, I typed xy. Okay, and then my r bar is the sum of those values. Okay, so in this case, the test statistic is 72. Okay, simulating from the null distribution. Remember, that's just the distribution of the test statistic under the null hypothesis, where the averages are the same, is easy by randomly permuting ranks. And our ranks just go from 1 up to n. Now it's a little bit trickier if your ranks have fractional components. Ours do not, because all of our data points are unique. But if there are fractional ranks, then you can't just permute the integers 1 to n. You get an approximation when that's what you do. There's a whole bit in the book about what you might do when you have fractional ranks, but I don't want to sidetrack us here. You get very similar results when you ignore the fact that there are ties in the ranks. But for more on that, take a look at the book. Okay, simulating from the null distribution. So random ranks, that's just sample 1 to n and n of them, right? Each one of these is just a permutation of the numbers 1 to n, which I interpret as ranks, and so they're samples of random ranks. So I just need to put that into a for loop. Let's do 100,000 samples. In my notes, actually, it looks like I do closer to a million. Why don't we see how long that takes? It probably doesn't matter. I need a for loop. Okay, so these are my random ranks, my random R, Y, X's. And then I'm just going to take the part of those that are the Y part. So those are the first NY of them. And then I'll sum them up. Those will be my R bars. Sum of R, Y, S. And I made space for the R bars before. So I'm good to go on that. Okay, so now I'm just simulating a million random ranks. That was pretty fast. The usual visual is a histogram of my samples representing the null distribution. You can't see that, so there you go. There's the histogram of my ranks, and then I can put on the plot V equals R, the actual one I calculated from the data, and there it is. Okay, then we can wonder whether that's an extreme value under that distribution, or we can calculate a p-value with mean of our bars less than or equal to r bar, and better multiply that 2 to get a two-sided p-value. So 2%, 2.2%. So we would probably reject the null hypothesis and conclude that the averages are different. Okay. So pretty easy, I think. Here's what's harder. So let's go back to the whiteboard. How about by math? So the distribution of the rank sum statistic, which you could call capital R bar, may be obtained by considering the distribution of ny integers selected without replacement from the total number of available ranks. So it's the number of different subsets of 1 up to n of length ny, and then you consider the sums of that subset. And so selected and then summed. Okay. So this is really just about counting. We have the total number of sets of ny subsets of 1 to n, and then we have the ones that sum up to our observed statistic, which in the example is 72. So that's part over a whole, and that's how you would calculate this probability. So the number of ways to sum ny from n things is ny choose n. Okay, so that's pretty easy. And then counting how many of those sum up to r bar, which in our example was 72, is harder. That's getting a little sloppy. That's what people call a subset sum problem. So you want to do a subset sum problem, summing up to r bar, integers ny selected from the set 1 up to n. And then you're going to go grab that and this, and then take ny choose n and put that into the denominator. So that would get you the probability of that event. Okay, so this is called the subset sum problem, which you can Google, and it has a Wikipedia page. It's NP hard in general, which is a computer science classification for very difficult to solve, but it's also very simple in concept. You're really just counting the number of elements of a subset that sum up to a particular number. So you can enumerate them, but it might take a while. See Appendix B3 in the book. Again, I don't want to get sidetracked. In a sense, it's easy because the algorithm is easy, and I provide some code for doing that. But in another sense, it's computationally difficult because enumerating all possibilities can be really slow. In R, you can, what you really want is the cumulative distribution function. So there is a cumulative distribution function called P Wilcox. It's a little confusing. This is the Wilcoxon with an O-N at the end test, but a lot of the things in R use the word Wilcox instead of Wilcoxon. But it's totally Wilcoxon, but you're going to use the P Wilcox function, and it works with a shifted test statistic. Okay, so it works with what I'm going to call R bar prime, which is the R bar that I calculated before, but it's getting shifted by its size, which makes some of the calculations a little easier. Okay, so over to R, I can do the math way, which is really just going to be me calling one function. So I'm going to do 2 times P Wilcox and give it R bar, but I'm going to shift it by ny times ny plus 1 over 2. And I have to give it ny and nx. And I have to put the star in the right place. Okay, so you can see that that p-value is very similar to what we calculated by simulation. So if you found that unsatisfying, check out Appendix B3. Read more about it in the main chapter in Chapter 9. Chapter 9 also has a central limit theorem approximation, which I'm not going to go over here. And it also has one more example. In particular, that example has ties in the ranks, which requires some special handling. So you'll find some details in there. That's all for now.